bi-weekly FNNDSC lecture series. So today our guest speaker is Ajay Rajaram, and Ajay is a senior PhD candidate in the Department of Medical Biophysics at Western University in London, Ontario, Canada. And he previously completed a Bachelor of Science in Medical Physics from McMaster University. And now his current research focuses on the development and clinical translation of an optical biomonitor for continuous measurement of cerebral perfusion and metabolism. And he has published 8 peer-reviewed articles, and 3 are currently under review. And he has presented his work at over 40 clinical and technical conferences. And now he holds a Natural Science and Engineering Research Council Canadian graduate scholarship. And today his talk title is Optical NeuroMonitoring of Cerebral Perfusion and Metabolism at the Bedside. Let's welcome him.
Awesome. Thank you. Hello, everybody. Thank you for having me, and thank you for that introduction. So my name is Ajay, and I'm wrapping up my PhD at Western in Canada. So throughout my degree, I've been really interested in optical neuromonitoring and applications in infants. So today I'm going to talk about a brain monitor that we built and translated to the clinic. And I'm going to focus on a few of the studies that I've spearheaded throughout my PhD. So just to give you some context, our work is done out of the London Health Sciences Centre in London, Ontario. Now, we're not the most popular London, but I'm optimistic that we'll get there. We're about halfway between Toronto and Detroit. So the Children's Hospital in London has about 120 beds, and that includes a 43-bed neonatal intensive care unit where some of our research takes place. So our hospital sees about 6,000 births a year, with about 500 of those passing through the NICU. So this little guy is one of the premature infants that was born at our hospital who was admitted to the NICU. He was born after 24 weeks, weighing a little over 700 grams, so about 3 months too early. Now, obviously, this guy is very heavily monitored. This is an image of the Philips IntelliVue monitor that sits next to his bed. You know, it tracks his heart rate, respiration rate. He's got an umbilical arterial line to measure his oxygen content. He's got a, to measure his blood pressure, and he's got his a pulse oximeter to measure his oxygen content. Obviously, among many other things. Now, the point of all this monitoring is to, catch any issues and track his progression. And now these metrics are effective at quickly assessing heart and lung function, but they're not specific to cerebral health, and they can't help us in speculating whether or not a brain injury may occur. And in the NICU, there is currently no continuous brain-specific monitoring in standard practice. So this infant was enrolled in one of our studies, and if you look to his head, you'll see some of the technology that we've developed to specifically monitor the brain and help address this gap. And this is largely what I'll elaborate on in my talk today. So you guys, better than most, would appreciate the importance of tracking brain development in such a fragile patient population. So I won't dwell too long on our clinical motivations. But our group has been interested in premature infants who are at the highest risk of developing a brain injury, such as intraventricular hemorrhaging, which is largely due to an underdeveloped and fragile vascular bed in the brain. And we know that the younger these infants are born and the less they weigh at birth, the higher the risk of developing such a bleed. We also understand that hemorrhaging is most prevalent within the first few days following birth. So our first criteria was to develop a bedside technique that could be implemented within this critical time period, and one that was capable of longitudinal monitoring. Now, a second interest of ours is with infants who have already experienced a bleed and are trending towards hydrocephalus and ventricle dilatation. Now, our center has many infants who undergo many procedures to minimize the buildup of cerebrospinal fluid, and which try to essentially mitigate any damage caused by brain tissue compression. So cranial ultrasound remains the current gold standard to diagnose brain injury. Clinicians can visually assess and grade brain hemorrhages, as you know. Ultrasound, however, is limited in its ability to continuously monitor. Infants usually receive their first scan within the first week of life, and then again at around day 30, unless otherwise prompted, usually by an irregular blood pressure or significant drops in hemoglobin. But it's also important to note that ultrasound images can only be used to detect injury where some amount of irreversible damage has already occurred. So from this, we just see that there's a need for a prognostic technique that could continually monitor these infants and inform clinicians of which infants are at the greatest risk of developing a brain injury, perhaps before significant damage occurs. So in this approach, firstly, we understand that there are physiological precursors to these structural brain injuries. Now, there's an amazing body of research in brain injury in both neonates and adults that teaches us that maintaining adequate oxygen supply and utilization is necessary to maintain cerebral health. So the ultimate goal is determining whether a patient has sufficient energy production. So that means cells are receiving oxygen and efficiently metabolizing it to create energy. If we have a significant reduction in energy produced, this can lead to cell death, tissue damage, brain injury, and long-term cognitive impairment, which could present clinically as anything from a cognitive or behavioral deficit to a motor disorder like cerebral palsy. So up until recently, we've only been monitoring surrogate markers of energy production. Our pulse oximeters in our clinic tell us how much oxygen is in the arterial circulation, but we have to essentially presume that that's delivered to the brain and turned into energy. Now, many more current studies have started to implement cerebral oximeters to directly measure oxygen content in the brain. And while these studies have shown that they can provide robust measures of cerebral saturation, they've still proven insufficient in describing the metabolic environment in the brain and insufficient in essentially predicting longer-term neurological outcome. But from these studies, we've learned that biomedical optics are safe and they're effective in monitoring the brain. So more recent improvements in technology have given us the ability to measure cerebral blood flow and metabolism using near-infrared spectroscopy. So we're getting closer to measuring what we're actually interested in, and we can make fewer assumptions along the way. So this is a picture of a NIRS system that my lab used to measure tissue oxygen saturation in the brain. This was back in 2011, similar to how a cerebral oximeter would. They could also inject a dye as a contrast agent and see how quickly that moved through the circulation, and this gave them a measure of cerebral blood flow. And finally, based on oxygen content and supply in the brain, they could calculate the cerebral metabolism. So they wanted to ask, when do changes in flow and metabolism actually become clinically relevant? So they used a piglet model of neonatal brain injury. In this graph here, each dot represents a different event. Essentially, the piglet's carotid arteries, which supply blood to the brain, were occluded to varying extents. And the piglet was left to stabilize, and then a measurement of the cerebral blood flow was taken, from which they calculated the metabolism. Now, from this data, we can see that small reductions in the flow from baseline did not impact the metabolism. Only past a certain threshold did metabolism start to decline. Now, neither flow nor metabolism are measured in today's neonatal ICU. So when I started graduate studies in 2015, we had the goal of developing an optical system that would be capable of continuously monitoring flow and metabolism dynamically and longitudinally at the bedside. And perhaps we could identify a similar threshold in the clinic, which could indicate the onset of a brain injury, once again, before significant damage occurred. So we improved upon our NIRS technology, and using NIRS, very simply, we can shine an infrared light into the brain and analyze light that propagates through brain tissue, from which we can determine the concentration of light absorbers. So in developing a system, we decided to use broadband near-infrared spectroscopy. Whereas most NIRS techniques use light at discrete wavelengths, broadband NIRS uses something like a white light source that spans all wavelengths in the near-infrared. It only requires a broadband light source and a spectrometer, like in the image I showed earlier. So it's a pretty simple system. It's relatively cheap, even compared to other advanced NIRS techniques, like time-resolved or frequency domain. But similarly, broadband NIRS can measure light absorbed by oxy and deoxyhemoglobin and calculate their concentrations in tissue and provide a measure of tissue oxygen saturation. Our lab analyzes reflectance data using a multi-parameter fitting. So essentially, we set certain boundary conditions and we fit for the tissue water fraction and hemoglobin concentrations. Now, one of the biggest benefits for using broadband NIRS is the ability to measure cytochrome C oxidase. So this is a diagram of the mitochondria. In the inner membrane is the electron transport chain, which performs oxidative phosphorylation to create energy for the cell. Cytochrome is the final electron acceptor along this chain, which becomes oxidized, and this drives energy production in the form of ATP. Now, similar to hemoglobin, we can measure the oxidation state of cytochrome C oxidase from its absorption spectrum and determine its concentration. And this provides us with a direct marker of cerebral energy metabolism. What's pretty cool is that NeRS was actually originally invented to measure cytochrome in vivo. Acquiring this marker has proven quite challenging over time since its signal is significantly smaller than hemoglobin. I've scaled cytochrome on this plot just for display purposes. But over time, it's become more feasible as technology and detectors and light sources have improved. So using NeRS, metabolism is actually more commonly calculated as CMRO2. And this is a calculated based metric using oxygen content and supply to determine oxygen utilization. The metabolism data I showed in that first piglet data set was calculated as CMRO2. Now, CMRO2 requires measurements from multiple modalities, and it therefore carries along with it any errors or assumptions that are made along the way. And this can be, you can calculate flow using Doppler ultrasound, using optics, or anything else. But when measuring blood flow, for example, no matter the modality, it's often challenging to exclude contributions from extracerebral layers. Conversely, metabolism via cytochrome is a direct measure, which is acquired using the Beard-Lambert law based on the light absorption, the path length of light, and the extinction coefficients, which are just from literature, but very similar to how we just calculate hemoglobin. Cytochrome is also a more brain-specific marker, since the concentration of cytochrome is significantly higher in the brain as opposed to the scalp. So we can much more readily attribute changes in the cytochrome signal to metabolic changes in the brain. But cytochrome does remain challenging to collect, and it's acquired as an absolute change in concentration, which also poses a challenge when trying to compare cytochrome values across different patients. So in addition to NeRS, we use diffuse correlation spectroscopy to measure the cerebral blood flow, whereas NeRS looks at light absorbed by hemoglobin. DCS focuses on light scattered by red blood cells. And just to describe it really briefly, when we shine a light into tissue, we can detect light that scatters off of red blood cells in the microvasculature. And as these red blood cells move, the light scatter changes. So we can simply use an autocorrelation, and we can see how quickly this scatter pattern changes over time. Essentially, the quicker this function decays, the quicker that the light scattering pattern has changed, and the faster the red blood cells are moving. And this gives us a measure of blood flow. So using NeRS, we can measure tissue oxygen saturation and metabolism via cytochrome. And with DCS, we can measure cerebral blood flow. So our goal was to build a hybrid broadband NeRS DCS system. This combination, however, was not completely trivial. As I said, our NeRS technique uses a broadband halogen light source, which spans a pretty wide wavelength range in order to best detect the spectral features of hemoglobin and cytochrome. DCS, however, uses a strong and very stable laser so that any fluctuations in the light intensity are attributed to the movement of red blood cells. Now, if we try to use these techniques concurrently, this results in oversaturation of the NeRS detector and inaccurate measures of the DCS from instabilities, both of which lead to inaccurate readings. So we overcame this issue by implementing a multiplexing shuttering system to just very efficiently cycle between NeRS and DCS techniques on the order of seconds. And this is a schematic of the hybrid system. So we've got the NeRS highlighted in red and the DCS in blue. We had 4 external shutters that sequentially blocked light en route to the patient and prevented crosstalk between the 2 different detectors. And with this setup, we can achieve really good signal strength using a 3-second NeRS, 3-second DCS shutter cycle time, with about a half-second delay to account for shutter transitions in between. In each technique, we currently use a 250 millisecond acquisition time. So over each 3-second period, we get to average 12 acquisitions. The trade-off here just being signal strength versus the temporal resolution. But we get a measurement of flow and metabolism every 7 seconds with this setup. So to demonstrate the system's ability to track transient changes in flow and metabolism accurately, after building the system, we used a piglet model of neonatal hypoxia-ischemia. and we used 8 piglets and had a couple controls. On the right, you can see one of the piglets with the probe holder that was one of our original designs to secure the optical fibers to the animal scalp. So here is some data from that study. This is a time course of one of the animals. Cerebral blood flow in black, and cytochrome, our measure of metabolism, is in green here. And you can see that cerebral blood flow here is in absolute units. We injected a contrast agent, indocyanine green, and measured the flow using NIRS, and then converted the DCS values using that metric into absolute units. So looking at this data set, at the beginning of region 1, we've clamped the carotid arteries to induce ischemia. And at region 2, we've reduced oxygen content to 8%, inducing hypoxia. So these, first of all, were very, very severe injuries, and you can see blood flow drop something like 90%. We wouldn't expect to see changes like this significant in the clinic, but it was a good demonstration of the system's ability to capture very dynamic changes. Now, there are a couple of interesting observations that we can make from this data. First is just looking at the overall change in flow and metabolism following the event. Flow has a hyperemic response, which recovers pretty close to baseline, but a drop in metabolism persists following the procedure. And we're really curious as to whether this immediate difference in metabolism could be indicative of the severity of the event. We also see a temporal delay in metabolism compared to flow. And both of these observations were consistent across all animals in our study. So here are correlation plots showing metabolism on the left and saturation on the right, both as a function of cerebral blood flow across all animals in this study. It was about 6. And from this, we can see that there's an almost linear relationship between saturation and flow. But in metabolism and flow, there seems to exist some threshold of flow beyond which metabolism is impacted. We saw significant changes following around a 60% drop in flow. Now, cerebral blood flow is generally compensated for by changes in the oxygen extraction, but this compensatory mechanism is only effective up until a certain point. When we see large changes in flow, they start to alter metabolism, and this can, lead to cell death, tissue damage, and subsequent brain injury. So we essentially wanted to take this idea and apply it in the clinic when we monitor infants. So the first step in translating our device to the clinic was to make the system that I initially built for the animal studies more suitable in human patients. Now, the original design was quite bulky and had a lot of components, so we simplified it to this. I minimized the design by using a NIRS light source and a spectrometer that had built-in shutters. I programmed the DCS to shutter digitally. And I also implemented a software correlator to analyze the light scatter data used for our flow measurements digitally. Even the optical probe size was reduced by combining the fibers. And then we housed the system in this portable cart, which we soundproofed. You can see some of the soundproofing on the door. We just wanted the system to run pretty quietly in the NICU. But most importantly, I named the system NNeMo for Neonatal NeuroMonitor. And here it is in action at the bedside. So NNeMo is a non-invasive brain monitor that provides the first continuous measure of cerebral perfusion and metabolism via the microcytochrome. And because it uses NIRS and DCS, it's obviously extremely safe, it's portable, and it's relatively cheap. So if you look at the laptop, you can kind of see that there's 2 different softwares running there. So I've programmed the NIRS and the DCS to run and acquire data simultaneously while analyzing the data sequentially, only during the appropriate shutter open periods. So on the screen, I'm looking at the light intensity spectra of the NIRS and the autocorrelation curves of the DCS, which indicate the flow. I've also written software to export the data as it's acquired and analyze it in real time. But I've essentially found it more useful to look at the quality of the data during the experiments. But we can get a measure of perfusion and metabolism on the order of seconds. On the right, you can see our optical fibers and our probe holder on one of our older infants. This was one of the bigger obstacles, was finding something suitable for, a very obviously fragile patient population. So I worked with a company called Lobtech in Germany, and we designed optical fibers that were really light and flexible on the patient end, while sturdy between the patient and the optical system, just for usage in the clinic. We've got separate NIRS and DCS emission fibers and a single detection fiber just to minimize space. And this is all the patient sees. So these fibers can bend light 90 degrees to reduce weight on the infant's head. and they reach about 1 centimeter in diameter. So they're pretty low key on the infant. Now on the system end, you can see that this single cable branches into multiple fibers, which connect to our sources and our detectors. We've got a NIRS spectrometer, and we've got 4 DCS detectors that we use to average the data to improve our signal quality. And all of this is housed within a closed system. So the patient only sees the patient end of the system. Now, finding a way to secure these fibers to an infant's head was the next step. So I wanted to make the design as small as possible. There's not too much real estate to work with, especially on a preterm head. And after a few iterations, this is our current design. So I drew this in 3D software and printed it in a light and flexible material. And we utilized an adjustable strap that's non-abrasive to an infant's skin. So I designed the holders so that they had a flexible arch. So it actually hugs the infant's head. And this allows us to maintain really good probe contact with very little pressure applied. And there's a very soft foam base there. We also have various sizes of holders that we can use based on the size of the infant being monitored. You can also see on the top right picture, there's a little white circle embedded in the holder. That's a Teflon disc that we use to scatter the DCS laser light. And this helps us create a larger spot size of light incident on the infant's skin, which just helps us with heat deposition. We're able to stay well within the laser safety limits, even more so since our light sources are constantly being shuttered on and off. But we do regular spot checks, and we haven't had any problems with skin irritation from the laser or from the holder itself so far. And we use a 2 centimeter source detector distance for DCS and a 3 centimeter distance for the NIRS to ensure that light's adequately interrogating brain tissue, which isn't a huge issue in the infants. So this might be a bit of a bold comparison, but here's our system next to the MetaOx and the BabyLux, which are both commercial optical monitors. Now, the MetaOx, which I'm sure you're familiar with from ISS, and the BabyLux is from groups in Europe, Italy and Spain. So our system uses broadband NIRS, while the MetaOx uses frequency domain, and the BabyLux has time resolve. So there are a couple trade-offs here. Our system can measure metabolism via cytochrome in addition to CMR02, whereas the others are currently limited to just CMR2. This could potentially change. The MetaOx has 8 wavelengths from about 660 to 830. So it partially covers the broad absorption feature of cytochrome, which extends to about 900, but this is still going to be a bit of a challenge, especially just with discrete sources. The BabyLux has 3 NIRS wavelengths, but time resolved NIRS has improved depth sensitivity since it's able to collect information on the photon time of flight, and it can use that to isolate later arriving photons, which have penetrated deeper in the brain. But these are some, highly vetted commercially available systems. And I've got myself into a little David and Goliath face-off here, but I'm staying in the game, so it's been going okay. So using NNeMo, we've monitored infants as young as 24 weeks gestational age and have no issues monitoring infants that are on phototherapy or CPAP. So our NICU has multiple stages of phototherapy to help prevent jaundice. The first stage is a UV light overhead, and the second is a UV blanket that's placed under the infant. And our fiber setup is sufficiently shielded so this ambient light doesn't impact our measurement. And in infants with CPAP or other ventilator systems, I've designed the probe holder with this in mind, actually, so it fits quite nicely under the CPAP equipment that our center uses. You can also see that we use phototherapy eye shields on all of our infants just as an extra precaution. So we've currently got 2 studies running in the NICU. The first, which has unfortunately been held up in the current environment, is recruiting all preterm infants at the highest risk of brain injury, those under 32 weeks gestational age or weighing less than 1,500 grams at birth. So for this study, I'm on call at the hospital, and immediately following birth and resuscitation, NNeMo monitors the brain for the first 6 hours of life. Infants in our study receive a cranial ultrasound to diagnose and assess cerebral hemorrhages, as well as an echocardiogram to observe any correlation with heart function. And this monitoring is repeated on day 3 of life to kind of better encompass this critical range where we start to see the development of a lot of hemorrhaging. Now, here are some very preliminary data that I'm still currently working on, but this was taken on the first day of life from an infant born at 29 weeks. The top 2 plots, we can see a fair amount of fluctuation in the cerebral blood flow in black and in the saturation in red. But by day 3 of life, these fluctuations have begun to diminish. And across both days, we see no significant drops in the metabolism. The few sudden changes that are depicted here are isolated motion artifacts. But in data like this, we're interested in looking at the extent and the duration of hemodynamic change and the impact on metabolism. For example, here we can see a mild desaturation event. So zooming in, we can see that blood flow drops by 40% and saturation by 10%. But this event was not significant enough to impact the metabolism. So in this study, we're essentially hypothesizing that if we see large and persistent fluctuations in blood flow, this will precede clinically significant changes in metabolism, both of which will correlate to the onset of brain injury. So our plan is to compare these fluctuations to clinical outcome with the ultimate goal of seeing if we could establish clinical thresholds of flow and metabolism. Now, these could be used as prognostic tools for assessing brain hemorrhages or to even help gauge brain injury severity, essentially after the fact. But we have a couple of interesting cases where on day 1, the head ultrasound comes back clean, but on day 3, we've seen the presence of a grade 2 or even 3 bleed, sometimes bilateral. So I'm really interested in seeing if a relationship results. Now, our n size is a bit small at this point to make any bold conclusions, though. So one of our setbacks is the same issue everyone's facing right now, really, which is patient recruitment. But this was actually one of my biggest concerns going into this study. Many of these births are unexpected and emergencies, and it can be a quite awkward time to approach parents when we're trying to monitor immediately following birth. But we've actually had a lot of success. The ultrasound images that we're taking are also delivered to the clinical team, and parents have been really receptive of that. Currently at our institution, we're still not allowed back in the clinic, but I'm working on writing up a paper just with the data that we've collected so far. But during our monitoring period, there's a whole lot that goes on, especially during the first day, between patient handling, various imaging, even mom and dad seeing the infant for the first time. So the 6-hour duration was actually initially chosen simply as a physical limitation for me to stand at the bedside and take note of everything that was going on. But our preliminary data is promising, so we're looking to extend this period on the order of days. And for some of these longer measurements, we want to be able to track motion. And we've been considering implementing an accelerometer to the probe holder. But we're trying to correct for motion in our analysis, which is also a big challenge. I've seen some really significant events in our infant data that unfortunately have a lot of motion throughout. There's been numerous arterial saturation drops of 40%, sometimes 50%, but understandably, there's a lot of patient handling surrounding these times. So we also have a second study in the NICU where we monitor infants who have already experienced a brain bleed and have a buildup of cerebral spinal fluid in the brain. So as the ventricles enlarge, intracranial pressure increases, brain tissue becomes compressed, and this can drastically alter flow and metabolism in the brain and cause significant long-term injury if left unchecked. So at our center, one of the first lines of defense is to perform a ventricular tap. So here, a pediatric neurosurgeon is inserting a needle into the lateral ventricle and draining cerebral spinal fluid from the head. Now, the timing of these operations is quite subjective. Our clinicians often rely on measurements like head circumference to dictate intervention. But you can see our system in the back there kind of clocking along during this procedure. As brain tissue compresses during the progression of hydrocephalus, and conversely, as it's given more room following these types of procedures, we were interested in looking at the extent to which vessels are occluded and how this changes as pressure is relieved, as well as the impact on brain tissue viability, which we could infer from our metabolic measure. Here I'm showing an average time course of cerebral blood flow during 10 ventricular taps, as well as a box plot indicating the overall change following the procedure. Now, the duration of the tap for each patient was different, so the time course data I interpolated to the average tap duration. But immediately following this procedure, we see a slight increase in flow, about 8%, which was supported by previous studies. During the same time period, we see little change in the tissue saturation, and we see a very slight improvement in the metabolism. This was the first time that flow and cytochrome had been measured during a ventricular tap. So it was interesting to see, and we recently published this work, but there's still a lot that we can build on from this. So the data in this study, first of all, were limited to only 2 minutes prior to and following the injection. And this was due to a lot of motion surrounding the procedure. There was surgical preparation, such as sterilization of the surgical site before the tap. And then following the tap, there was often a lot of patient repositioning almost immediately. So we were really limited in only seeing the immediate effects of the tap. So one thing I want to look at is longer term measurements in the days and the weeks surrounding ventricular tap. If we can gauge how flow and metabolism change en route to hydrocephalus, perhaps we could see if these physiological measures could provide a better indication of when a tap is required, or even how much cerebral spinal fluid the clinician should be removing. Also, in this study, we didn't account for cortical mantle thickness. So if an infant's brain was compressed to the point that our light was interrogating the ventricles and interrogating the CSF, it could impact the results. We've actually done previous work in our lab where we've collected samples of the CSF from the infants and used that in our fitting and accounted essentially for the light absorption of CSF. And finally, we work with a group in London that specializes in 3D ultrasound. And here's a scan from one of the infants in our study. On the top, you can see a single slice of a lateral ventricle being segmented. And on the bottom, you can see the 3D reconstruction. Now, there have been studies looking at ventricle size and hydrocephalus, but we're interested in directly comparing changes in ventricle volume to metabolism, which we believe would be a better indicator of clinical outcome. So I'm currently heading one more study in the clinic, and this is in a very different patient population, but it's still pretty relevant. So I was approached by an anesthesiologist at a different hospital in London who works in the cardiac operating room, and he was interested in monitoring the brains of adults during surgery with cardiopulmonary bypass. So during cardiac surgery, the heart's arrested and the bypass pump takes over the function of the heart and the lungs. An issue persists with ensuring that the brain is adequately perfused. There's a high incidence of post-operative neurological complications, cognitive decline, increased risk of stroke, and the like. But in this study, we had 7 patients. I recently submitted a paper on this. It's currently under review. And we monitored them with NNeMo throughout the entire operation. And in retrospect, if I knew we were going to monitor adults so soon, I might not have named the system the Neonatal NeuroMonitor, but here we are. Either way, this was a nice test of our system's robustness. We were able to have very minimal noise in the extremely bright surgical environment, and we had strong signal quality, even when dealing with the increased skull thickness in adults compared to the neonates. So kind of getting right into it, here I'm showing data during the transition on cardiopulmonary bypass on the left, and during the transition off cardiopulmonary bypass on the right. This is just for a single patient. So the first plot, the one at the top, shows the bypass pump flow rate. The Philips monitor measuring the mean arterial pressure data is displayed on the second plot, and that was at a radial site. And the DCS measure of flow follows, and the NIRS measurements of cerebral saturation and cytochrome. So from this data, we can see when the heart is arrested, which is done using a potassium solution, the flow rate is increased, the pump flow rate is increased to maintain adequate perfusion. So let's look at the third plot, the blood flow. Just by looking at the range of values, we can see the flow transition from pulsatile while the heart's beating to non-pulsatile as the pump takes over. This is also apparent as the patient's heart is restarted following the operation. Across both of these transitions, we see little change in the saturation and a slight decrease in the metabolism when going on the pump. Going off the pump is a lot less eventful, which kind of suggests a pretty smooth transition when restarting the heart. This is data, the same data, but this is across all patients in the study during the transitions on and off bypass as shown in the box plots. The table I've included has a middle time point, 15 minutes into bypass. But firstly, looking at the cerebral blood flow, we can see that flow is consistently overestimated by the pump when first going on bypass. Perfusion to the brain increases almost 90%. And this is obviously more preferable than under-perfusing the brain, but perhaps intraoperative information like this could help aid perfusionists in selecting more patient-specific flow rates. Current values only change across patients based on their actual size. We also saw significant decreases in mean arterial pressure and in cytochrome during the transition on. But it is important to note that when the bypass pump, it's initially filled with a crystalloid solution in its reserve. So the first pass when the bypass pump is turned on is void of blood, and this causes a hemodilution effect. So the changes that we see in metabolism are likely a combination of real changes in metabolism, which have been shown in previous literature during similar situations, but as well as a perceived change in metabolism from manipulating the optical properties, replacing the hemoglobin essentially with this crystalloid solution. But these changes largely diminished 15 minutes into bypass, and they're essentially gone during the transition off bypass. Another really interesting aspect to these operations are the hemodynamic events that occur when patients are fully reliant on cardiopulmonary bypass. Many of these are dictated by sudden and extreme changes in the bypass pump flow rate, most often for surgical reasons. So the graph on the left here is a stable period. The bypass pump is on, and we can see that stability reflected across all these metrics, which are measured using 3 different modalities. Now, in the same patient on the right, we have a series of reductions in the pump flow rate. This was actually following a successful valve replacement very close to the end of surgery. This subject experienced a sudden tear in the aorta just above their new valve,